So now we have an expression for h of s that includes one term that has a simple transform, and these are looking like they're close to the transforms of trig functions, but not quite. So let's sort out exactly what we need. So the transform of a function like e to the at cosine bt, the transform of this guy is s minus a over s minus a squared plus b squared. And you'll notice neither of these are quite in that form, but they're not far off. So to fix it up, we need to complete the square in the denominator and turn it into an expression like this, and then we have to make sure that the s isn't alone here, that it has a minus a, whatever that a value turns out to be. Same thing for the transform of e to the at sine. The difference is that, well, let's put that down. So the transform of this guy will be similar, except the numerator is just b. Okay, so clearly neither of these are quite in the right form, but they're not far. So let me just tuck these away on the side. And let's try and figure out how to get them into the right form. So here we have 1 over 10 times 1 over s. Now the transform of this guy is straightforward. 1 over s is the transform of a constant, so this will go, when I invert it, this will go back to 1 over 10. And here, I'll leave the 1 over 10 out of things for now, and I'll leave the s in the numerator for now, and in the denominator, I need to complete a square. So what do I need on this part to make it a perfect square? I have to add the square of half of the coefficient on the s. So that's 1. So I need s squared plus 2s plus 1. But then I have 10 here, so I only have to add 9 more. And now I have something that will work out to a perfect square, at least part of it, and then plus 9 is the b squared left over. And then in this expression, 1 over 5 times, I'll do the exact same thing, but now actually I'll go one step further and write down s plus 1 all squared plus 9. In fact, I'll write that explicitly as 3 squared because we know that that's going to be our b value. So we can copy that over and fix up this part of the denominator, because that we now know is exactly s plus 1 all squared. There. Okay, so what's missing? Here you have an s minus a. We need an s minus a in the numerator as well, and we don't have that. So how do we modify this fraction so that it is there? Well, we have to do it in a way that doesn't change the value of the function at all. So if we were to subtract, well, in this case it's actually adding because there's a plus 1. So we want to add 1, but then subtract it off again. And you'll notice now I have an s plus 1, but there's an extra minus 1 in the numerator. But because this expression here is the same as this one here, this denominator, but there's a 1 over 5 in front of it. Let's do this a little bit more carefully then. So let's rewrite this as 1 over 10 times 1 over s minus 1 over 10. And now I'm just going to separate these out as two separate fractions. And then minus minus is plus 1 over 10 times 1 over s plus 1 squared plus 3 squared minus 1 over 5 times the same. Okay. So this one is taken care of. So I can get rid of that. And now you see this is a perfect transform of an exponential times a cosine. But we have this extra stuff over here, which is close to, but not exactly, the transform of e to the something t sine something t. So first of all, these are exactly the same term, and I have plus 1/10 minus 1/5, so I can just add those together, and I will get minus 1/10 overall. And I can get rid of this now. And this is almost perfect, except we want a b in the numerator, a 3 right here, which we don't have. So what are we going to do? Let's place a 3 there, but then we also have to divide by 3. Put that over here. And so now this is exactly the same value as it was before, but I have this section here of it is the transform of exponential times sine. So now I can take inverse transforms of all 3 terms, and I'll get h of t, which will be 1/10 times 1/s. The inverse transform of that is just 1/10. Here my 1/10 stays out in front, and the inverse transform of this guy is e to the minus t, where the minus 1 comes from this shift here, multiplied by the cosine of 3t, because of the b squared here, that's the 3. And then I have a minus 1/30 times e to the minus t, as in the other term, multiplied by sine of 3t. And that is the correct h of t, inverse transform of the function we started with at the top.